So chapter 7, we're going to deal with some applications of integration. I guess that's what it's called. And so the section 7.1 is dealing with area between curves. So I'm just going to start us off with an example, and we'll get somewhere with it. He just ran away. So find the area bounded by two functions, f of x equals x squared and g of x equals square root of x. Okay? So when we're actually going to start dissecting this problem, you realize it's a very simple Calc 1 question when we get to the end of it. But it usually helps to, well, sketch the region that you're trying to find. So if I sketch these both curves, here's the square root of x, and here's the x squared. I mean, it's a full parabola. But really the area that we're going to concern with is this guy. Right here. Okay? You got that?
Yeah, just letting you subtract.
Right, that's what... Well, I mean, because logically speaking, you just think about just basic geometry. First of all, it would be very helpful if we know from what to what, right? I mean, that's should be pretty obvious in this one. What is this point right here? 1, okay. So really, if you think about just basic geometry and just moving shapes around, you can always take, you know how to find this area, right? This area right here, the red one. This is the area under the square root function. Do you know that? What would that area be? How would you find that area? So it's the integral from 0 to 1 root x dx. Right, that's the big red area. Do you know that? And you know how to find this little guy. This is what? This is the integral from 0 to 1 x squared dx. So how would you find the one that's just really making it messy here, but you know, this thing? Well, we'll just subtract big from, I mean, small from big, so you just kind of subtract that, right? That's really all there is to it, right? I mean, you can just combine it into one integral, because the integration is linear. And really, that's what we're going to end up with. This is the outer function, you know, the function that's on the outside, and this is the function that's on the inside. Subtract small from big and integrate. That's about it. I mean, this is a Calc 1 problem. And it just feels right, just the way the geometry works. I mean, you know, big area, you know, the small area, you know, find what's left. You just subtract the two. It feels very good. and it will feel that good. There's no catch. Well, well, it will be a little more, you'll see some issues, but this is generally the idea. Is that okay? I mean, we can get all scientific about this, and I'm about to do that. So I don't know how much of this you want to be writing down, but we're looking at the problem. We're trying to find an area of a shape that we're not exactly familiar with, geometrically speaking. So when we're trying to channel our inner calculus person, when you look at the shape, you're trying to find the area of it, you don't know how, what do? Yeah, slice and dice it, right? So I'm going to take this thing, I'm just going to chop it up into a bunch of little rectangles and so forth, right? So first of all, that means I need to take my interval, whatever the interval is from A to B, right? So I need to figure out what delta x is, which usually is b minus a over m. That's how you did it in Calc 1, right? You take your interval, you find its length, that's b minus a, you divide it by n, how many rectangles you want to do, right? So what is the area of which one of these rectangles? This side is delta x, right? What is the length of that side? Well, it's the square root minus x squared, right? So it's, in our case, it's one function. So in our case was this. So the height was g of x minus f of x, and the width is delta x, that's given by b minus a over m. Okay? So the area of one of those rectangles would be g of x minus f of x delta x, right? Length times width. So then if I want to start adding all of those rectangles, so I need to add them up, so we do something like that, right? It's from 1 through n, so this is g of x of I, whatever your partition is, left point, right point, that won't matter, as you know from Calc 1. Delta x. Yeah. Thank you. To make this area actual precise, you want to take a limit as n goes to infinity, right? That's what makes it an area. So what the limit does, it stretches the sigma into an integral and changes delta x into dx, right? So that just an integral from a to b, g of x minus f of x dx. Oh, I'm just kind of proving it more precisely. That's all I'm doing. I'm just deriving this formula. We got that formula just by intuition, and we're exactly right. But we have to be careful with our intuition in math. So this is being more precise as far as I'm just showing that you're still going to come up whatever the bigger function minus the smaller function, and you integrate from it. And it felt good, and it's good, and we're good. Okay? But this is how you do things, right? I mean, when you're trying to find an area of a shape that you don't know, we're going to slice it and dice it into the pieces that we do know. In the next section, we're going to try to find the volume of something that we don't know, so we're going to slice it and dice it into pieces that we do know how to find the volume of, and then we're just going to add them together, take the limit, sigma becomes integral, and we'll have some nice. Okay? With me? Very, this is good. So now the rest is very technical, just computing that integral. So it's from 0 to 1, x to the 1/2 minus x squared dx. That's what makes it easy. So the rest is, right? I mean, you should be very happy with the way this problem is going right now. So what does it give me? X to the, what? 3/2, so 2/3 of that, right? Minus x cubed over 3 from 0 to 1. Is that right? Plug in 1, you get 2/3 minus 1/3. Plug in 0, you get 0. So that's 2/3 minus 1/3 equals 1/3. So this, oh, whatever. Yeah, so these are just, arbitrary unit system. So whatever your x is measured in or whatever. You know. It's 1/3 units. Well, sure. Yeah, it's an area. Good. Well, what if never mind. What if it's in acres? I don't need to go acres squared, right? It's 1/3 of an acre. Oh, well, you don't know what I'm measuring x in. Maybe I'm measuring x in something else. But you're right. Anyways. Too technical, but it's good. Is that all right? Does that make sense? So usually our biggest issue in these types of problems will be finding these points of intersection. They'll involve some algebra or trigonometry depending on our functions. This is what we're going to be hang out the most, finding the limits of integration. Okay, so let's do this. Find the area bounded by f of x equals 2 minus x squared and g of x equals x.
And you showed us like how to use it or do it using sigma.
No. You know how to integrate. You know how to find the, area and all that. You don't need to do the sigma. So let's sketch this. 2 minus x squared is an upside down parabola. Moved up to units, right? And x is just a line that goes through the origin. Is that okay? So we're looking for this area right here, area of this shape. So right now the integral, what's our upper function? Right, so it's 2 minus x squared, and then the lower function is x, so minus x dx. We just don't know the limits of integration. Yes? Yeah, just set them equal to each other, right? That's when the y values are equal to each other. So to find the limits of integration, we have to solve this equation. And if we do, this is a very simple quadratic. If we move everything to one side, so it's x squared plus x minus 2 equals 0, factors nicely. X plus 2, x minus 1 equals 0. So these are my limits. So this is -2 right here. So we'll just be integrating from -1 to 2, 2 minus x squared minus x dx. Yeah, that way around. Sorry. Is that okay how we found that? How we set that up? Any questions on that? I mean, the rest is straightforward. We'll just integrate that. There's nothing to it. So what do we get? You plug in 1, 2 minus a third minus 1/2, and you plug in -2. What do we get? -4 plus 8/3 minus 2. So distribute your sign, so, I mean, you get something. 9/2? Okay. I think that's what I have. Yep. Mm-hmm. Any questions? Yes? You can say that, yeah, because that's the only thing that'll happen. Yep. So yeah, you can get that later. Other questions? This is nice. Let's try this. Area bounded by y equals sine x and y equals cosine x. That's the thing. We need to figure that one out, right? Well, no, let's just do like, the first, yeah, just the first chunk. Yeah, like from 0 to 2 pi or whatever, yeah. Okay. So I mean, if we just do the sketch, yeah, so just from 0 to 2 pi. So this is the sine curve, and the cosine curve is what? We have pi over 2, and 3 pi over 2 as zeros. So it's like that, right? So we'll be integrating sine x minus cosine x. Is that right? Now what are the limits? Right, so you can use the symmetry. I mean, we know this point, don't we? When sine equals cosine, that's pi over 4. And then you use the symmetry of the graph, so this is pi over 4 in that direction. So you have to subtract pi over 4 from 3 pi over 4, and you get 5 pi over 4, right? Peter, is that what you said?
Yes.
Are we okay how we found those points? mean, you can set it up, sine equals cosine. Gets a little, I mean, how would you just solve that equation analytically without using the graphs? Does anybody remember? Yeah, you can, again, this is kind of what we did. You can do it on the unit circle. Yeah. How would you do it just, analytically, algebraically? What? Yeah, but I mean, yeah, so then you're always going to refer to a unit circle. I mean, you're looking at pi over 4, symmetry, 5 pi over 4. So there's, I mean, you can square both sides, convert sines into cosine, set it up as a quadratic, and solve that. Still do the same thing. Yeah, you really want to use unit circles for that. Right. Yeah, you're still going to use the unit circle at some point. Well, I mean, yeah, you can. I mean, in a lot of ways of doing that problem. It's just, yeah, just unit circle, do the graphs. There's no cute way. I mean, there is a cute way, but it's all counterproductive. So let's do that. What's the integral? Is that right? Right, so it's negative cosine x minus sine x. Is that right? Right. Right. So plug in some numbers. Negative cosine of 5 pi over 4 minus sine of 5 pi over 4, then subtract. So it's plus cosine of pi over 4 plus sine of pi over 4. Is that right? So what do we get? Negative 1. So make it positive 1, right? Minus another negative 1 plus 1 plus 1. So what is it? 4? That's not. No. Sorry. It's gone crazy here. Yeah. Never mind. I don't know. Being crazy. So yeah, those are a bunch of root 2's over 2's. Yeah. So it's 4 root 2's over 2. So that's 2 root 2 over 2. Yeah, that's better. So yeah, so that's 4 of those, right? So 4 root 2 over 2. So just 2 root 2 over 2. I'm sorry, just 2 root 2. This wasn't good. This is number 20 out of your book. So the region bounded by y equals negative x cubed plus 3, y equals x equals negative 1, x equals 1. So it's the region bounded by all of that. So we kind of have 4 curves, but 2 of them are. So we have a negative cubic plus 3. So it looks like this. This is the cubic. This is your line, y equals x. And then you have a line x equals -1, which is a vertical line. And then you have x equals +1, which is a vertical line, right? It actually cuts it through here because it goes up to 1 and this is 2. So you have this shape. So how would that be any different from what we just did? Hmm? Well, I mean, but do other two functions even affect my integral? I mean, they just tell me, just give me the limits of integration. That's about, because they're vertical. So all I need to do is just to go cubic minus the linear from -1 to 1, right? So that's really what happened. I'm not going to be solving anything. I'm just doing the integral from -1 to 1, -x cubed plus 3 minus x. Okay. Minus x dx. Yeah, because I mean, again, when you look at the shape, all these functions, they just give you a shape. And then you just look at the shape, and you happen to have a vertical line here and a vertical line there. So you just say, well, just from everything that we've done, is the upper function minus the lower function. Well, what are the bounds? -1 to 1. If other two functions were something more interesting, then we're probably going to have to, if you have a shape that's more weird, you might have to chop it up into pieces and set up few integrals. I might do that next.
If x equals 1 is more of a diagonal line.
Yeah. Yeah, you'll have to chop it up. You don't have that symmetry. I mean, those are not the same, right?
Well, that area from 0 to 1 underneath x is the same as the area above x from 0 to -1.
Oh, you mean these two things? Oh, well, I mean, I don't know how that's... Yeah, those are the same, but...
So if you integrate just x cubed plus 3, it's going to be the same. From 0 to -1.
Yeah, you can... Yeah. Very good observation. Whatever makes it go smoother. I'm not going to do the integral, whatever that is.
6.
6? Okay. Let's try this one. This one is a little more fun. This is number 42 out of your book. So, sketching these things.
Just out of curiosity, if you didn't sketch them, like how do you figure out which one?
It will be actually, well, that's what was mentioned earlier, that, if you have a simple shapes like that, I mean, if your area comes out just negative, that means you kind of,
And could you can't just...
Well, if it was just like a simple area like what we just dealt with, when it's just always, when one function stays above the other functions throughout the integration, then you're either going to get a positive answer, or if you flip it, you're going to get a negative answer. But in this case, we're actually going to see where at some point one function stays above the other function, but then they switch, and then they switch again. Now we're not trying to integrate, we're trying to literally find the area, okay? So there we have to be really careful, because at first there's going to be like one above the other, but then they'll switch. So I will really have to sketch and see. You can do some interval testing, find the zeros of intersect, but you're just better off just sketching. And when it gets complex like that, you can pull your graphing calculator and really see what happens. Well, let's do that. We can do this by hand. We'll have to factor. Let's pull a calculator. So what was that thing? So what was the first function? And what was the other function? What was the other function? Cube minus 4x. So what's going on here? At first, from -2 to 0, you have a cubic above quadratic, but then they change. You get, not the quadratic, the even one. Then they switch, and then they switch again. Well, I want to do from -2 to 0, and then from 0 to 1, and then from 1 to 2. I want to find the entire region bounded. Okay? We can grab this by hand. We can find those points of intersection by hand. It's not that hard. I can do that. Right, it's 3 different intervals. So yeah. But they're all simple, right? So we'll set this up. So what did we say? It's a cubic? Cubic minus the fourth, then fourth minus the cubic. Right, so we'll go the integral from -2 to 0 of the cubic, subtract the, and then plus, what was that, from 0 to 1? The other way around. And then plus from 1 to 2? Okay. Well, again, you're just looking which one is above, okay? Which one is above? So if I go back to the graph, and this is why I did the different color thing. See, like I look at this first region. See, basically the thing here, what happens is they kind of switch. The red one stays above the black, but then the black above the red, right? So that's what you're doing. You're doing above minus, higher minus lower throughout the integration. Do we want to do this by hand? Why not? Tons of algebra, sketching is going to be a little bit painful, and especially like analyzing what stays above. Well, actually, it wouldn't be that hard because you know that one is going to cross. Yeah. But it's doable. So, no. Okay, good.
At every intersection, would you know that they switch? Or, because I guess they could just contact, right?
Yeah, but usually, like with this kind of polynomial thing, they'll just
You had x squared on there. Like if we just barely touch where the w, you see where the w was.
So this is the point that you have to be very careful. A lot of times you just have to kind of test those intervals and just see which way is which. Owen, did you have a question?
It was basically the same as Dalton.
Okay.
Like you would account for, like if you had that, and then you had like, I don't know, like the parabola basically that went out, and then like 1/2 x squared, like fully went beyond the x to the fourth. Like so, it's just like kind of across, but it intersects
Uh-huh.
w, and then and then you took the limits integration from like -2.
Well, I mean,
It would account.
yeah, if one function would just stay above the other or equal, I mean, the equal part doesn't matter, so it'll still work. Um, yeah, we did a tons of algebra on that in my notes. Um, I can do this just to show you that it's doable, but I agree, I don't want to do that. Yeah, we did some, some hardcore factoring. You're finding your zeros, you're sketching both, and then you do, find the points of intersection. So you set both of those things equal to each other. You solve that. You're finding your solutions. 3 integrals, and I really don't want to do the integral. It's a little boring. It's a Calc 1 integral, so done. You're not allowed to say that, by the way. Yeah, you can do something. Well, just Calc 1 polynomial integral. Just compute that, suffer through the process. Because it will take me half an hour to get through all the fractions. Okay?
Pretty sure you could not do plot as like an area.
Well, I mean, you cannot do that. That's cheating. So, okay. Let's see. So that was the last example in section 7.1 that I wanted to do. So you kind of equipped, well, that was fast. So you kind of equipped to do the homework.
What was the
What was
final
it?
answer?
In my notes,
64
yeah, and then I think that's when even in class I said, I'm not going any further, I don't care. So it's negative 64 fifths plus 64 thirds. I don't even know whether that's true, because we were just messing with that. Here's one example that we need to consider doing. Here's an example that's interesting. I want to find the area bounded by x equals 2 minus y squared and y equals 2x plus 1. So the sketch will really help us out here. I mean, and again, don't be lazy, do your sketches, they'll help. So 1 is straightforward, right? Y equals 2x plus 1, that's a straight line, intercept is 1, slope is 2, so whatever that is, right? What about the other one? X equals 2 minus y squared. What is that? So, well, it's a sideways full parabola, starting at 2. No, you don't have to. It's bounded by this curves, whatever. And is it gonna go out or in? Right. So it's gonna look. How's it gonna look like? So it's right. Is it gonna? What's gonna be the y-intercept? The square root of 2, right? So it's a little bit. It's a little bit like that, right? So I want to find this region, the area of this region. So there are two ways to go about this problem. Just before we want to start talking about limits of integration. But when I look at this, if I do it the way we've been doing it so far, kind of going upper minus the lower, so at first, at some point, my upper function becomes something else, right? At first, I'm between the line and the parabola, but then starting from this point, it becomes one half of the parabola and the other half of the parabola, right? So my upper function becomes something completely different. So I would end up solving for y in terms of x. I'll get plus square root minus the square root. So I'll have to be integrating the positive square root minus the negative square root, right? You see what I'm talking about? If I just go like that, vertically. But if I look at this picture this way, if I look at this picture horizontally, if I start slicing and dicing it this way, basically, you know, I'm staying consistent, right? I'm always between a parabola and the line. You see what I'm talking about? So it's probably easier to look at this problem like that. I'm probably going to end up with a dy integral, right? Because now my dy is the change in y. And so I'm going to actually think of both of those expressions where x is a function of y. Right? I'm looking. Do you see what I'm looking at? I can probably rotate the whole thing and we'll just be starting over again. But
And then this other one, so integration, you plug.
yeah, you just plug.
X in, or you plug x in for the original, or for the 2 minus.
Yeah, you can do that way. But do you see what I'm talking about? Because if I look at this way, all I have to do is to integrate. The upper would be the parabola, so it's 2 minus y squared, minus the lower. So I kind of have to solve for x in terms of y, right? So I will have to solve for x in terms of y. So what do you get? Yeah, so y minus 1 over 2, so is that 1. Right? Now to find the limits, those in terms of y, so as Owen was saying, you can just make this substitution, just take x, plug it in here, and solve for y. So that will give us y equals 2 times 2 minus y squared plus 1. So it's not going to be pretty, is it? Y equals 4 minus 2y squared plus 1. So when you move everything to one side, 2y squared plus y, that looks like a negative 5 equals 0. No, it doesn't factor, so use the quadratic. You're going to get something really, something unpleasant. So what is that? Negative 1 plus or minus 1. So what is it? 4ac, what is that going to be? Minus 40 with that minus, so it's plus 40 over 4, right? So it is, yeah, negative 1 plus or minus root of 41 over 4. So these are your two limits, minus and a plus. So really you're integrating from negative 1 minus square root of 41 over 4, and then negative 1 plus the square root of 41 over 4. And clearly that's a Calc 1 problem, which you can totally finish on your own. I don't feel like messing with that at the moment. Yeah. I mean, on the test, if something like this comes up on a test, you're almost allowed to say, yeah, the rest is, just integrate this. On the homework, you should self. Yeah. So we just, I'm just wondering if we stick with the dx integral, will it be, maybe we'll have two integrals, but prettier limits, maybe? You know what I'm talking about? Yeah, you'll have to solve for x. Maybe the x values are better. You know what I mean? The y values will still be the same, but right. But then since, yeah, but what if it's like x is one? Well, which I seriously doubt it. Probably won't work like that. But, if you go the other way around, if you do that substitution, you get, don't write this down, but it says x equals 2 minus and then 2x plus 1 squared. So this is x equals 2 minus 4x squared minus 4x minus 1. Is this right? Close enough? No. Yeah, it doesn't. You get some magnitude. So, okay, good. But you got the idea what's going on? So sometimes if you have a shape that's kind of choppy, you can flip it. Maybe, I don't know, what?
Oh no, it's under the square root of the quadratic, you have 25. I thought it was minus 16, but it's plus 16.
Yeah, that's not working. Yeah, I don't think you, I mean, just looking at that, it's negative 4, probably not. No, no. Yeah, it's not ugly. Okay, good. Okay, so 7-1, nothing special. So let's talk about volumes a little bit. Okay, this is the exciting part. We're gonna, so this is kind of, we have a lot of time left, so I'm gonna 7.2-ish intro. Talk a little bit about volumes, and you will get heavy into volumes in Calc 3. You'll be able to do some really nice volume problems because in Calc 3 you will be given an extra set of x's. You're going to have x, y, z, 3 dimensions. So you're going to have certain surfaces, and then you look at the, if you integrate over a surface, you instead of area, you're going to put the volume. So you're going to have a nice ways of doing volumes. But Calc 2, just like Calc 1, is still calculus of a single variable, so we don't get the z-axis yet. But we can still think about the volume and we can kind of do a walk around the issue of missing the third axis and moving into the 3 dimensions. And what we'll be doing for now, it's nothing, I mean, it's nothing all that special, but we'll be doing problems like this. You have a curve, whatever, there's a function. And I'm just going to take this curve and then use our imagination and pretend that we're going to rotate that curve around, let's say, the x-axis. So you take that little chunk and you start rotating it around the x-axis. So that's basically taking this entire region and you'll just rotate it around the x-axis. So, that's a little circle and that's a little, circle. So you end up with a kind of a cute little vase, right? So we'll be getting a lot of things that are symmetric because we're just going to be rotating. I mean, eventually we can take a shape that is between 2 curves and rotate that around the axis. You might get a vase that's hollow or whatever. You can take one little curve and rotate it around an x like y equals x thing. Just rotate it sideways. You'll get some cute little shapes. Okay? But Maybe we'll get a nice little result today that's very sassy. Because, one of the, and I think that came up, we really like the formula, the volume of a sphere, do we? Didn't we mention that already in this class? What is this? Archimedes? 4/3 pi, what? R cubed. And if you don't allow, if you don't know this basic, like the integration methods that we know, this becomes really frustrating challenge to prove that the volume of a sphere is 4/3 pi r cubed. Has anybody here maybe read a book or seen that proof that Archimedes did?
I've looked at it. It's a sphere like inside of a cylinder, and it's the difference between the sphere and the cylinder.
Right.
That he uses to calculate.
And the way he proved that, he was slicing those shapes and he was putting them on a kind of on a balance beam of sorts. It's like, on this side I'm going to put a sphere, like on a cone, and on that side I'm going to put a cylinder, and they will balance if I move the center of balance like 2/3 that way. And it was just, and there's a nice fun proof of that. We might do something like that in math club or whatever. Huh? Okay. So this is a fun little thing, but after you do that, he comes up with the following formula. A geometrical formula is that if you have a sphere of radius r, okay, what is the height of that sphere? 2r. And so then you take a cone that has a radius r here, and it has the same height as a sphere. So it's a cone of the height 2r, but the radius is 2r. So it's 2r by 2r kind of cone. And then you take a cylinder that's of radius r, also has the same height, 2r. Okay? So it's kind of 2r by 2r cylinder. So after playing with that scale, he comes up with the formula of that. It's kind of cute. Now, I'm not going to drive that formula. No, it's we'll do it in a math club or whatever. It's too fun for Calc 2. We cannot do that. But, so proof of that, this is where the money is, and this is why he was all proud of that, and that's on his tombstone. Hey, realized Archimedes responsible for that. But now, the rest should be simple, right? The unknown is the volume of a sphere. We do know the volume of the cone, right? The volume of a cone is 1/3 pi r squared h. So you get 1/3 pi r squared, and h happens to be 2r, right? And we know the volume of a cylinder, and actually we'll use it today. The volume of a cylinder is just, the area of the base times the height. So the volume of a cylinder is pi r squared times h. Right? I'm doing something wrong here. No?
Because you end up with 2 pi r cubed over here, you subtract 1/2.
Right. That's 2 on this side. Good. So then the volume there is pi r squared times 2r. So then, yeah. So it's volume of a sphere plus 2/3 pi r cubed equals pi r cubed times 2. So then you subtract 2 minus 2/3 is 4/3. Good. This part is the simple part. Deriving this is kind of fun. I hope we can do this. We'll get this one in a more calculus-y kind of way by the end of the day. Okay? All right, so let's do some theory then. So going back to what I was just talking about, rotating things. So let's say I'm going to take a very simple case. I have a pretty little function. Let's just call it f of x, and it's bounded from a to b, like that. Just took a chunk of it. I'm just going to flip it around the x-axis. I'm going to rotate it so it makes, how does it do like that? That kind of shape. Okay? So when I find the volume of that. So now, I'm looking at the shape that's geometrically challenging, and I don't know the simple formula to find the volume of that shape. So what do I do? Since I took Calc 1 and paid attention half an hour ago, slice it and dice it, right? I'm going to slice it into pieces that I know how to find the volume of. And something that comes to mind feels like, well, if I just slice it like that, what do I get? If I just take a little slice in the middle, okay, this is not coming out pretty, but can you visualize what that kind of slice is? It's a little tiny, skinny, short cylinder, right? I mean, if I took this thing on the side, it's going to look like that. Little cylinder. So when I slice it, again, I'm going to take the width here to be delta x, and delta x is, as before, b minus a over n. Okay? So that's the height of that cylinder. Delta x. Okay? Now, from the previous story, the volume of a cylinder is the area of the circle, the area of the base, times the height. So I just need the area of this circle. The area of the circle is pi r squared, right? Well, what is the radius of this thing? It's just precisely the height of the function as the value of the function. Do you agree with that? The radius of that circle is given by the function itself. Do you see that? So at whatever point, call it x sub I, doesn't matter those sample points. So this is pi f of x sub I squared. Okay? So when the volume of this little cylinder is pi r squared times the height. Is that okay?
Can you explain the right-hand side of
That side? Well, so all I need to figure out is the radius, right? So just think about this. If I take this thing back where I got it from, so it's sideways. So this is the radius. This is the radius. Well, the radius is precisely the value of the function at that point, right? At any given point, the radius of that cylinder is given by the value of the function. You see that? So I'm replacing radius with the function. Is that okay?
Isn't there, so you can do it this way with the cylinders, but then there's another way, like if you revolve it around the y-axis,
Yeah.
it uses like peel off there.
Right. You literally like peeling off the orange. Call it shell method.
Yeah.
We'll do that one too.
Okay, because I did this in like high school calculus or something.
Nice. Yeah.
So
So there are two ways of doing that. This is called the disk method, and there's a shell method, depending on which book you read. So we'll do that one too. I mean, because like in this particular problem, you're better off slicing that way. But again, depending on the shape, sometimes it's better to go the other way, and sometimes it's better to kind of fill it from the inside out. It will be pretty challenging here because you kind of like this way you'll bound it between. But yeah, there'll be cases where one method works better than the other, and there'll be cases where both work. I'll actually ask you, here's one, do it both ways. Okay, you'll get the same answer, but there's cases where one is just, they're basically the same, but there are cases where one is really easy and the other one is, virtually impossible. So we'll have those two. But for now, we're okay how we found the volume of this one little cylinder, disk, whatever you want to call that. So we're going to add them all together. So this gives you a sigma. So the volume itself will be the sigma as n goes from 1, I'm sorry, as I goes from 1 to n, pi f of x sub I squared delta x. So that's the sum of the finite number of cylinders. You want to get the volume to be exact, we take the limit. N goes to infinity, that's infinity in there. So that just becomes an integral. So what is it going to be? It's an integral from a to b, pi f of x squared dx. I can pull the pi out, pi is the constant. So the volume is pi times the integral from a to b f of x squared dx. This is a nice little formula. Disk method, then your book calls it that. Well, sometimes you do, but you basically what you're doing, you're increasing the radius kind of thing. You know, you're building it from the inside out.
Like our future space, like if you have like a towel roll.
That's precisely what you're doing. So you'll be finding the volume. Basically, you're doing. Yeah, you like. Right. I mean, you as you said, the paper towel, right? If you unfold it, it's a rectangle, but it has a tiny height. That's a delta, whatever. So it's the area of a rectangle. So it's a height, the width. The width is the circumference of that, and then the delta x is there. So we'll get a little more messier formula. So 2 pi will show up because you're talking about circumference. So it's 2 pi r. But then you'll be messing with the radius. Okay, so this will be the rotation around the x-axis. What? I don't know. I'm having an off day. I should have been a doctor. Look at that handwriting. Now, if you rotate around the y-axis, you'll get the same thing. You'll have f of y dy. That's the thing. With a shell, it's different. If you rotate around the x, you actually end up with a dy integral. But if you rotate around the y, you get a dx integral. So that's going to be the thing. Which way is easier to look at those functions? But rotation, okay, I'll be more precise. Rotation around the y-axis, you'll get the same thing. Whatever your limits from c to d, doesn't matter, pi f of y dy. So same formula, just depending on your variables. Squared, right, just need to square it. Thank you. So let's just do a few examples, and maybe we'll do a circle. Well, you're definitely right as far as visualizing the process. It's pretty straightforward here.
Yeah.
But with the shell, you have to, it's a little different. It's more imaginative, a word like that. Okay, so let's try one. I want us to do a region bound. No, not that one. So we're going to take this function, y equals the square root of sine of x, and just rotate it around the x-axis. And we, of course, there's some domain issues with that one, right? Because the sign will stay positive from 0 to pi, right? But then becomes negative, so I shouldn't be, doing the square root of that. So we're just going to do it from 0 to pi, okay? Because that's when it stays positive. Now, what is the graph of that going to be? I mean, what's the graph of that? I mean, not 100%. All I know is it's going to be pretty symmetric, staying above the x-axis, right? Because, you know, if this is the sine, you know, this is just the sine from 0 to pi. So the square root will definitely share this point and that point, right? But then how is it going to be? So when you take a square root of a number less than 1, you actually get a bigger result, right? Like square root of 1/4 is 1/2. So it's probably going to be like something like, I don't know, maybe a little fatter like that. I'm not saying it should be having like that kind of a bump, but it's going to be a bump. But generally speaking, kind of the same thing. Yeah. Yeah. I mean, it should be. That's what I was going for. Well, let's, I mean, I don't know like if it has the square root. The square root, maybe. Sine of x. So yeah. See, but if I do just sine of x, so you see sine of x stays just a little bit below. Right? But anyways, just looks like sine. It's about all. So we're going to take that thing, we're just going to rotate it around. So I don't really need to do anything else because I have the formula. The formula suggests from a to b f squared dx. And this is the case where we're actually happy to see a square root. Right? Isn't that square root makes us happy in here? It's from 0 to pi. And it's just a square root of sine x squared dx. So the square kills the square root. Otherwise, we'll be stuck with just a sine squared. And if you remember from day one, those are challenging integrals. We had to do some half-angle formulas or whatever. So this is just the integral of pi times from 0 to pi sine x dx. Is that right? So what do we end up getting? Yeah, it's going to be 2 pi in the end. What's the antiderivative? Negative cosine x from 0 to pi. So you plug in pi, you get negative of negative 1, right? You plug in 0. But it's, yeah. And when you plug 0, you get 1, so it's minus again negative 1, so it's 2, so 2 pi. That's it. You just kind of need to know the formula. The formula is pretty straightforward. Again, if you forget the formula, just the volume of a cylinder, that's all it is. Okay? Dx is the height, and then it's pi r squared. Any questions on this? Again, for the graphs, you can use a graphing calculator, whatever, if you're stuck on those.
And then you also have it where like it's like revolving around the line.
Yeah, we'll do those too. Like, let's say I want to drill a hole into it, so I'll just rotate it like here's a 1/2. So I'll just cut that piece and I'll just rotate it around the x-axis. I'll have a hole, or I can just rotate it around 1/2. So I'll have this kind of a twinky little thing, right? So you know you can have fun with that, and we'll get to that. We're just doing very basics for now, but yeah, we'll do all that. Here's another one. Region bounded by y equals x cubed and y equals 8. So region bounded by x cubed, 8, and the y-axis. And we will rotate around the y-axis. So graph, just a quick sketch. You have a line y equals 8, so it's this. You have the y-axis, so it's that. And then the x cubed, so it's that. Right? So that's the region. And we'll rotate it around the y-axis, so you get like a bowl like that. Right? Just rotate it that way. So the limits of integration, since we're doing the y-axis, is going to be dy integral. The limits are 0 to 8. So right away the volume is pi integral from 0 to 8 dy, but my function is supposed to be a function of y, so I should probably solve for x in terms of y to get my function in terms of y. It shouldn't be a big issue, right? From here, x equal cube root of y, right? So that's what you integrate, cube root of y squared. Which now is a Calc 1 problem again. So that's pi from 0 to 8 y to the power 2/3 dy. So what's the so what do you get? Y to the power 5/3, so that's 3 pi over 5 from 0 to 8, right? So you plug in 8, you get 32, and that's it. So it's 3 pi over 5 times 32, so 96 pi over 5. Mm-hmm. 96 pi over 5. And that's it. Any questions on this?
You had said instead of bounded by the x-axis, you had said bounded by y equals 1 to drill a hole out. Or wait, x equals 1 to drill a hole out.
Yeah, so to drill a hole out, you just, again, you're looking at what are the radius. So the radius is always between, you know, it's a cube root of y minus 1 at any instance, so you square that. Okay. But let's do the sphere. I want to do the volume of a sphere. So we're going to prove in a newly discovered way the volume of a sphere. And a nice way of doing that, if you think about it, is to getting a sphere through rotation. Well, you can do two, because I mean, I can do a semicircle, right? I can do this thing, the semicircle, right? And I can rotate it around the x-axis. What will I get? If I just rotate that, I'll get a sphere, right? So if I just think about the circle of radius r, centered at the origin, so it's x squared plus y squared equals r squared. So again, if I want to do the around the x-axis, if I solve for y squared equals r squared minus x squared, so y equals plus or minus the square root of r squared minus x squared, right? And since we're trying to rotate the upper semicircle, we're going to do the plus. I mean, you can rotate the bottom, so it doesn't matter because you're going to be squaring it anyway. But is that okay? So we'll be integrating this function, that's the radius of our disks, squared. Yeah, well, from -1 to 1, but then we can do the symmetries, right? Because that's, you see the symmetry, right? But right now, but yeah, sorry, from -r to r, you're right. From -r to r, pi and then our function, so square root of r squared minus x squared dx, right? So since this function is even, I can do the trick. I can just say, well, this is just double. It's a double of the integral from 0 to r of r squared minus x squared dx. Are we okay with that, what I just did?
Can you take the r out because it's a, so what could you can separate them and then wouldn't the integral of r squared be constant?
Yeah, r squared x. I mean, I can split them into two integrals. Won't make a difference, really, as far as the computation. But are you okay with what I did with the 2 and a 0? Because it's an even function integrated over symmetric interval. Instead of going from negative to positive, I just go from 0 to positive and then double it. Is that okay? This is your Calc 1 trick. I mean, you've done it in Calc 1. But anyway, so the rest should be pretty straightforward. So it's r squared x minus x cubed over 2 from 0 to r. 3, that's right. So we get 2 pi, and then what? R cubed minus r cubed over 3. And then 0 is 0. John, is that right? Well, what? That's r squared x, and I mean, I'm just integrating. So that just gains an x, and this is just cube over 3, right? Because r is a constant. Okay, so I think we're done, right? It's 2 pi times 2r cubed over 3. Is that right? Well, x, r went in for x, right? Because I'm actually integrating. So I'm replacing every x with an r, because that's my limit, right? So you put r in here, you get r squared times r, that's r cubed. And when you put zeros, it's all gone. So yeah, so 2 times 2 is 4, so it's 4/3 pi r cubed. Volume over sphere. What? Yeah. You should know what it is. I'm doing this on purpose. I'm saying 2 so you catch me, so it's a 3. It's all big part of the plan. You have to decipher my scribbles, because you know what I'm doing. You should be able to not copy it down, but redo the math. Because it's a pretty straightforward math as far as integration goes. The setup, that's something new. But hey, we got 4/3 pi r cubed. Okay, good. I'm done.